Hello! It's hard to believe we're already on our third unit of chemistry. This unit is on the electrons, just like last unit kind of focused on the atom in general and the properties of matter and the nucleus of the atom. This unit here will focus mainly on the electrons and what electrons do and why we can see different things because of electrons. So our first lesson is going to focus on our atomic model. Actually, we're going to talk about ions a little bit more later, but just kind of looking at what are the two atomic models that we're going to primarily use. So the curriculum goals, if you look at the North Carolina Standard Course of Study, are the essential standards. There's two goals that we're going to be covering or discussing. Analyze an atom in terms of location of electrons. We're going to get into that more and more specifically through this unit, and explain the emission of electromagnetic radiation in spectral form in terms of the Bohr model. Right, tonight we're just really going to focus on the Bohr model, and we're also going to talk about quantum mechanical model. In the Bohr model, an electron circles the nucleus in fixed energy ranges called orbits. It can neither gain or lose energy inside that orbit. It can move up or down to another orbit. And the lowest energy orbit is the one that's closest to the nucleus. So what are they talking about? Well, this is Niels Bohr's model of the hydrogen atom. It's also called the Rutherford-Bohr model because Bohr and Rutherford worked together on it. Hopefully the people presenting them will kind of explain that. So Niels Bohr described that the electrons of an atom, they're having orbits around the positive nucleus, so they're moving around it, kind of like solar system. Now this is not our current model of the atom, but it is very useful to describe a couple of ideas, things that we see happen with electrons. Now what happens with electrons is they're orbiting the nucleus. They orbit at as low an energy level as they can, as close to the nucleus as there's room for them. And when they're at their lowest level, closest to the nucleus, it's called the ground state. Now, the more electrons an atom has, the more energy levels fill up. There's only room for so many electrons in each orbital, in each orbit, in each energy level. The letter N stands for the energy level, and the number of the energy level can be anywhere from 1 through 6. So let's look at that on a picture. Here's a nucleus. The nucleus is positively charged because it has protons in it, and the electrons go around the outside in these orbits. Now the first one, level 1, will hold a maximum of 2 electrons. Level 2 will hold a maximum of 8 electrons. Level 3 will hold a maximum of 18 electrons. And then levels 4 through 6 each hold a maximum of 32 electrons, and we didn't show those in this particular picture. So each energy level will hold so many electrons, and they'll hold them in little areas called orbitals. We'll get into the orbitals a little bit more day after tomorrow. I think Friday is the day we're getting more into that. So what happens with electrons? Do they stay in that one place forever? Oh no. Electrons can absorb energy and jump to a higher energy level. They can only go up a whole level. They can't go up part way. So they have to give enough energy to take them all the way up to a next level. This is called absorption, when they absorb energy and jump up. Now when they're at the higher energy level and they're all jumped up to a higher level, they're said to be excited. So if you hear someone talking about excited electrons, that doesn't mean they're out of the ball game going, yay, 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 we're so excited. Or they're about to go to Disney World and they're like, whoa, 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 we're so excited. What it means is they absorb some energy and they're at a higher energy level than their ground state. Now they can drop back down to a lower state. When this happens, they release a certain amount of energy in the form of light. They release a little piece of light. This is called emission. So that if they go from a high excited state back to a lower state, a little piece of light comes out. The light we see comes from this process. All of it. All of the light we see comes from excited electrons going to lower energy states. So this is kind of what it looks like. You can have, at the ground state, it can absorb some energy and jump up to another state. It can absorb a lot of energy and jump way up to a high state. And then when it goes back down, it releases energy. So it can go up and down from ground state to different excited states and back down and back up. And the electron can just jump all over the atom. So when absorption occurs, when it absorbs that particular amount of energy from light, there's only certain wavelengths of light that can cause an electron to go up a whole level or to go up a couple of levels. So only certain wavelengths of light can do that. When emission occurs, only certain wavelengths of light are given off. And we're going to kind of go into tomorrow that these wavelengths translate to our eyes as colors. So we can tell what element's present by the colors of light that are either given off or taken in when the electrons have been excited. Now the amount of energy it takes to move an electron is called a quantum of energy. It's the amount of energy required to move an electron from one energy level to another energy level. So you may have heard of quantum mechanics or quantum physics. That has to deal with little packets of energy. One packet of energy in particular is a little packet of light. One quantum of light is known as a photon. So photon is, we see billions of photons when we're seeing light. Billions of photons are hitting your eye, hitting the rods and cones in the back of your eye. And your brain translates all that energy as visual signals. So if you drop down, excited electron drops down, becomes a little less excited, then blink, a little photon comes off. If a little photon comes in and hits that electron, the electron sucks it in, it absorbs the photon, it absorbs the energy and jumps up and becomes excited. So this is what we would see. We may not see an individual photon, but we can see colors of light that are absorbed by elements or emitted from elements. So the colors of light that we see absorbed here, this is an absorption spectrum, you'll see as dark bands. So if you look at a spectrum of light and you see little dark bands, that's because the elements in there are absorbing those to make the electrons excited. The elements in the substance is producing the light. For emission, you're going to see just bands of color. So that means that as the electrons went from an excited state to a ground state, they let out exactly this color, or they let out exactly that color. Now these particular lines are from hydrogen atoms. Hydrogen atoms are the one that we're going to focus on primarily for studying how excited electrons release light. So the hydrogen atom in particular is the one that the Bohr model is used for, because it's very simple, it just has one electron. And we know, if we know what energy level an electron and a hydrogen moved from and to, then we know what color light's going to be emitted. What color light we're going to see is going to depend on where that electron moves. So we're going to look at the reference table and see what happens if an electron in hydrogen moves from the fifth energy level, n equals 5, to the second energy level, n equals 2. You have this reference table with you at home, hopefully. I handed it out a couple of days ago, so feel free to look at it while we're kind of going. Actually, let's do n equals 6 to n equals 2. Okay, so here's the reference table you got, and you see that it has the energy levels labeled. This is 1, this is 2, 3, 4, 5, and 6. So this is where the electron can be, in one of these energy levels. And we just said we wanted to see what would happen if it went from 6 to 2. So first, let's find, that should be a 6. Okay, so first let's find the dot on the circle that's labeled n equals 6. So we've got a dot here that's on the one that's the outermost, the n equals 6, and we've got one here. So it's going to be one of those dots that's our electron that's going to go from an excited level to a lower level. And we said we wanted to find where it went to 2. So we have to see which one of these ones that's on 6 has an arrow that ends on 2. So that one ends on 2. This one ends on 3. So 3 is this line. That one just goes down to 3. But this one goes all the way from 6 down to 2. Okay. So next we just see, now that we just see there's one arrow that goes from 6 to 2, sorry, I had to fix that too, we need to see what number's under it. That's the wavelength of light that's emitted. So the number that is touching that arrow is the wavelength of light that's emitted. So the number that's touching this arrow is 410. Next, we need to see from that 410, what color is that? It's visible light. It says so right here that it's visible light. So to figure out exactly what color it is, we need to go back down here to our spectrum. Now, up here it's in nanometers, but down here it's in meters. So to go from nanometers to meters, which is what these measurements are in, we need to divide by 10 to the 9th, because 1 meter is 10 to the 9th nanometers. So 410 times 1 meter over 10 to the 9th nanometers gives us 4.1 times 10 to the negative 7th meters. Now that number isn't exactly here, but it's between 4.0 and 4.2. So any wavelength of light that's between 4.0 and 4.2 we will see as violet light. So the color of the photon that's emitted when an electron jumps from 6 to 2 is violet light. You can see there are other possibilities. We can have infrared light, which we can't see, and ultraviolet light emitted, which we also can't see. But we do have instruments that can record that and see when ultraviolet light or infrared light is emitted. And we'll talk more about the spectrum tomorrow. So for elements, every element has characteristic light that it gives off when its electrons are excited. So when you do a flame test, which we're going to do in class on Thursday, you can see the elements by the color of the flame. You know what element it is by the color that the flame turns. And we'll also look at spectral lines, those emission spectrum, using a tool called a spectroscope. And with the emission spectrum, you can see the bands that we were just talking about with the spectroscope. So different elements the electrons become excited and we see different colors of flame. This is how fireworks work. Fireworks are different colors because the different elements, when their electrons get excited, as they go back down to their ground state, they release different colors of light. Magnesium in particular gives you a very bright white light. We might do that tomorrow. We might save magnesium for another day. So when we use the Bohr model really only works for hydrogen, because hydrogen just has one electron. That's all it's got to jump around to the different energy levels. So it's very easy to follow that one electron as it gets excited and as it moves back to the ground state, because there's just one. For other elements, we really have to use a more complex model. We're going to get into this in a lot more detail come Friday and Monday, the quantum mechanical model, because the electrons aren't just simply in rings around the atom. They're in a much more complicated series of places. And it's really, there is still in energy levels, but they're not in fixed circles around the nucleus like the Bohr model shows them. So like everything else in life, it's not so simple. So this is a picture of the quantum mechanical model and a couple of the first orbitals that we'll talk about. This is going to be more in lecture 3, that we're going to get into this particular topic, looking at how these orbitals work. But these are not exactly where the electron is. but this is where the electron is most likely to be. The funny thing about electrons is you just saw the second it absorbs a photon of light, it jumps. So just by looking at it, by shining light on an electron, you move it. So you can't ever know exactly where the electron is because the second you look at it, you move it. The second you shine light on it, it jumps to somewhere else. It becomes excited. So we can really just predict where the electron probably is. This is one of the things that kind of drove Einstein a little batty because he didn't like having to use probability in trying to describe the universe. But if some of you are in AP Stats or plan to take it, probability is very important in describing the physical world because a lot of times we don't know exactly. We can just know what's likely. Okay, to summarize, light comes from electrons and atoms. Go figure. The wavelength of light can tell us what element there is. And also it can tell us how far an electron moved, whether it moved from a high energy state to a very low energy state, or if it just moved like a little bit. Now the Bohr model is very useful to describe how this works, because it's very easy for us to say, okay, an electron's on this energy level, an electron's on that energy level, even though real life is more complicated. So hydrogen is really the limit of the usefulness of the Bohr model. The quantum mechanical model is the model that we currently use that is best supported by the evidence, and it's used for all larger atoms than hydrogen. So we will talk more about that later. We're going to be doing flame tests later on this week. We may just practice some with the Bohr model tomorrow and then get into the flame test, or we might just jump right in and do the flame test tomorrow rather than waiting until Thursday. I'll think about it. So I will see you tomorrow. Hope you have a very good night.